Okay, so let's continue, probably. So now we are going to continue talking about general relativity, which also will be important for numerical relativity lectures. And last week, the last lecture of the last week, we introduced the basics of general relativity. Yeah. So basically, we first introduced the covariant derivatives for vectors, which basically means that we take the partial derivatives and add some new term which has this connection coefficients here, and which should, transform according to some transformation rule in order for the covariant derivative to be a tensor, right? And if I, instead of a vector, I take the one form here, I just change the minus, the sign here, with minus sign with the same connection coefficients, which basically means that if I construct some scalar quantities, and for scalar quantities, my covariant derivative is just the partial derivative. And actually, yes, I mean, if you take some kind of other tensors, like with several indices, then you put, several terms like that, each one for one index here, or with minus sign for each index downstairs. And if you do it accurately, then actually, it's kind of convenient, because if you have, let's say, some tensor like that, direct product of two vectors. If you calculate that by definition, then you have some partial derivative plus one term like that for alpha and another term like that for beta. And actually, you can also do it like you usually do with the partial derivatives. You can either take differentiation of the first factor, or you can leave the first factor and take differentiation of the second factor. And of course, that's for sure true for the partial derivative part. And also, like here, you have like two terms like that here. And one of them you get from this term on the right hand side, another one from this term. So basically, you can use the usual rules of differentiation, and that's kind of convenient, of course. And as we discussed last time, yeah, in principle, you can introduce these kind of things just by considering like curvilinear coordinates in a flat space, and you can also do that there. But otherwise, yes, you can have some arbitrary manifold, and you can introduce some arbitrary connection there. And there are several tensors which you can construct. Like one tensor is called torsion tensor, which is the antisymmetric part of the connection coefficient. Another tensor is the Enamelicity Tensor, which is basically the covariant divergence of the metric. If you have a metric on your manifold, like usually in jar we assume that torsion is zero, so that's the torsionless connection or symmetric connection. And also we assume that the non-metricity is zero, which means that the connection is what they call metric compatible, metric connection. And we also put it to zero. And in principle, even if you put both of them to zero, you can still have something more general than just flat space and curvilinear coordinates. And the thing which shows you that your space is not just some flat space and curvilinear coordinates is this guy here, the torsion tensor. Yeah. We had a look at that like from two different points of view. One point of view is that you can take some kind of closed loop, and you can parallelly transport the vector. And if the torsion tensor is not zero, it means that upon the parallel transport, you get some another vector, some angle. That's one thing. Another thing is that you can try to calculate the commutator of two covariant derivatives acting on some vector. And if your torsion tensor is not zero, generically you get non-zero result here. So the covariant derivatives do not commute. Yes. Sorry? I said torsion? Yes. Sorry. No, I didn't want to say that. So if you have non-zero curvature, then it's not zero. Actually, if you want to apply that to a scalar, then if it is non-zero, it means non-zero torsion. But that we are not going to discuss. So we put torsion to zero, non-metricity to zero. We only have curvature. And non-zero curvature means that this commutator is not zero, acting on a vector. If you act on something like with more indices and moreover, it will be not zero generically. If your curvature is not zero. And what I also did last time, I showed how you can derive that if your connection is symmetric and metric compatible, then you can derive that your connection must be of this shape in terms of the metric tensor, which is called Levi-Civita connection. And that's a connection we use in general relativity. Okay? I mean, in principle, like all these things are kind of quite simple in a sense. You know, all these formulas are nothing special. And but yes, if you are doing some concrete calculations, that might be difficult because, for example, here, the metric with upper indices by definition is the inverse matrix to metric itself. So generically, your metric is some kind of arbitrary, non-degenerate 4x4 matrix. And then to calculate the Levi-Civita connection, you have to find the inverse matrix. So that might require some effort. Okay. In principle, you know, if we look here at these connection coefficients, I mean, in the first lectures, we also discussed like gauge theories, like also Young-Mills fields. And if you look at this here, actually there is some similarity because you can look at the connection coefficient as like some differential one form, which like takes values in the space of matrices with two indices alpha and beta. And then basically what you have here looks very much like, you know, the field strength of Young-Mills fields, like partial connection minus partial connection plus the commutator of two matrices here, mu matrix and mu matrix. So that's very similar to the usual Young-Mills story. Okay, good. So that was the basic geometrical introduction. And then what we have, what I can also mention here is how I wrote this formula here. It was like very Killjoy style because I really, you know, took care of the position of indices here. So this definition of the curvature tensor is all right even if you have some non-zero torsion. If my torsion is zero, I don't need to, you know, to keep track of the position of indices here. It's just symmetric. Yeah. And actually, yeah. And here, you know, this mu and mu is precisely, you know, these indices which are related to the differentials here. So basically, you see mu and mu, it's always antisymmetric on them. And here I have like mu staying, or nu staying by the partial derivative. Or otherwise, mu and mu, they go like the left-hand side lower index here. And that's my definition. I put the derivative index to the left in the connection coefficient. Sometimes people use another convention, putting like that to the right. Okay, but anyway, for us it won't be very important, the position of indices downstairs here, because we always assume our connection is symmetric. And then after that I can define the Ricci tensor, which is contraction of the Riemann tensor. I take the upper index and contract with the middle one from downstairs. In principle, of course, I could also do that with the right one, just because it's just antisymmetric, I would just get minus the same thing. Or I could take contraction with the first index downstairs, but for Levi-Civita connection it's just zero. Because for Levi-Civita connection, the Riemann tensor is also antisymmetric in the first index. Okay, so that's the Ricci tensor, and then I can define the Ricci scalar, or curvature scalar, like that. For that I already need metric. And then, yes, if my connection was Levi-Civita connection, this one here, I can check that if I construct this kind of tensor, which is called Einstein tensor, then the guy automatically has vanishing divergence, vanishing covariant divergence. That's independent of equations of motion. It's just some abstract statement which is always true. Unless you made some mistake in your calculations, if you have some Riemannian geometry, which means geometry with Levi-Civita connection, you construct this kind of tensor, it must have zero divergence. There is no way around. And then, as we discussed last time, basically then the Einstein equations is that the Einstein tensor is 8 pi g, that's just some constant, multiplied by T mu nu, where T mu nu is the stress tensor of matter, right? And the important thing is that usually, like when we have our usual models, we have conservation laws, like the divergence of the energy momentum tensor is 0. And yes, we expect that generically in curved space-times it would be the same, but with the covariant divergence. And that means that the equations are kind of well defined. Both sides, they have vanishing divergence, so you can solve the equations. Okay, so that was the result of the last lecture of the first week. Yeah. Now we have to discuss a bit more. And first of all, in theoretical physics nowadays, we usually do not just write down equations of motion. We usually write down some Lagrangian. Yeah? Like we act in terms of the Lagrangian mechanics or Lagrangian field theory. So, which means that I need to find some kind of variational principle, some kind of thing which, for which the condition of vanishing first variation gives me the equations of motion like here, right? So let me first think about vacuum case, no matter, just pure gravity, for which I should find, the variational principle which gives the equations of motion that the Einstein tensor is equal to 0. Okay? So then the question is, what kind of thing might I find for that? Yeah? And then, usually we have some Lagrangian or some action, which means like I have my action equal to whatever things. Like for example, for scalar field, like something like that, yeah? So what do I have here? I have some integration over 4-dimensional space-time, and I have some scalar quantity here. So nowadays, first of all, I need to find out what kind of integration measure I can have, so that it's kind of diffeomorphism invariant, so I can change the coordinates, and what kind of a scalar I can put here. Yeah. So the answer to the first question is kind of simple. The integration measure is like, first of all, let me define G without indices. By definition, I say it's the determinant of the matrix G mu. And then here I can put square root of minus G, and that's my measure of integration. In principle, of course, I could put also any kind of constant coefficient here, but that's just some kind of convention to put just square root of minus G. And of course, that's just the usual measure if my G is just Minkowski, for example, and just 1, the usual integration measure. Why do I put here minus sign? Is because the determinant is negative here, and I don't want, of course, to have imaginary units. And in principle, our convention was to have plus, minus, minus, minus signature. So that means that my 4x4 matrix has 1 positive eigenvalue and 3 negative eigenvalues, so its determinant is negative. Even if I would choose here opposite convention, like minus, plus, 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 it would be like 3 positive and 1 negative. Anyway, it's negative here. So for even dimensional space-times with 1 time and odd number of spatial directions, then it's always negative here. So I always put minus sign irrespective of my signature convention. And then the next question is, what kind of scalar could I put to this integral here? And you already know an answer in a sense that we have found one scalar. And that's actually the simplest possible scalar you can construct on the metric. Non-trivial scalar. Of course, one more thing you can do like G mu nu, and that's equal to 4. But that's not really interesting, right? So basically you can put here the scalar curvature. And then that's some kind of well-defined expression which you can try to make variation. And let me first say that I put here minus sign and 1 over 16 pi g. For now, it's not important for me which kind of number I put here. the minus or plus sign here depends on the chosen signature. In a sense, you usually want to have positive kinetic energy for gravitons, and then what kind of sign you want to have here depends on your convention about the signature. So this guy goes like for plus, minus, minus, minus. If you have the opposite convention, it will be plus here. Okay. So then what I'm going to discuss now is how could you see that variation of this kind of action would give you the Einstein equation. So that's what we want to do now. Let me write it again. Okay, forget about the 3-factor. And I have here like d for x square root of minus g r mu nu g mu nu. Okay. That's this guy here. Okay, let me also say that, you can find some different usage of words here. Like, strictly speaking, if I put here like 4-dimensional integration, it's the action. If I remove like integration over time and leave only 3-dimensional integration over space, that's basically my Lagrangian, and the integration of Lagrangian is what we call action. If I remove all the integrations, it's kind of Lagrangian density, if you want, yeah. And how to define density, people also sometimes include square root of minus g explicitly, sometimes you do not do that, but finally, you should be careful what you do here. In a sense, if I mean like, without square root of minus g, it's just a scalar. If I take square root of minus g, it gives me some kind of density. Density is something which also changes like this square root of minus g. Okay, so I remove this circle, and let's see how can you do variation. I mean, one question is how I do variation inside the Ricci tensor, and actually I even don't need to do that, and I will come back a bit later to that. So another thing is that I can do variation with respect to g mu here. That's kind of trivial. I mean, at least if I do variation with respect to inverse metric. If I do variation with respect to the metric itself with lower indices, then it's a bit more difficult, but also not so much difficult. I mean, what you can do, you can remember that those are just inverse matrices to each other, right? So if you multiply one matrix by another matrix, it gives you the unity matrix, right? By definition. And then if you do the variation, then the variation of this guy multiplied by this guy plus this guy multiplied by variation of this guy should be variation of something constant, which means 0. And then you can just find out what is the variation of this guy in terms of variation of this guy. Yeah? So you can easily find that the variation of g mu with upper indices is minus g mu alpha, g mu beta, variation of the metric itself. So yeah, you can play these games, and that's kind of quite simple. Another thing to know is to how I do variation of the determinant of the metric. That's a bit different, and the answer is the following. Like if I let's say if I do the variation of the determinant, that should be equal to determinant itself multiplied by g mu nu, variation like that. And I mean, how you can do that? You can say that the derivative of the determinant with respect to the element g mu nu is equal to determinant itself multiplied by the inverse element here. And how you do that? I mean, if you remember like some linear algebra, how you find the inverse matrix. Basically, you take the element g mu nu, you find it's like algebraic complement there, and then you derive by the determinant. So which means that if I take this derivative and derive by determinant, I get another inverse matrix element there. So that's some kind of simple simple consequence of the usual linear algebra, nothing more. You just have to remember how you calculate the elements of the inverse matrix, and then it's kind of simple. And if I want to do like another way around, if I want to calculate the variation of the determinant with respect to the variation of the inverse metric, then you can either use this stuff here, or you can just use that, this determinant for the inverse metric is like 1 over determinant, right? So then you have another thing. And then you can calculate it like that. You will find it like minus g multiplied by g mu mu, variation of the inverse metric. So, yeah. And another thing, if you have square root of minus g, then it's kind of simple, right? Because you have square root of this guy, you take the derivative of square root, you have 1 over square root, you have also 1/2. And then basically you get like minus 1/2 square root of minus g, g mu nu, variation of the inverse matrix. So that's the only not absolutely trivial thing you have to take into account. And then after that, it's very simple to do the variation there. Okay, maybe before I do that, let me also mention the following thing here. Because this kind of variation here multiplied by the same matrix, basically, it's kind of an interesting point. Because suppose I want to calculate the divergence of a vector. How do I do that? It's just the usual covariant, the usual partial derivative divergence, plus I add this kind of term, and I have to contract mu and mu. Yeah? So I basically get like mu alpha alpha. And that multiplies a mu. Yeah? That's how I can calculate the covariant divergence of a vector. And then if I have this kind of guy here, I look here, and so what should I do? I should take put mu equal to alpha. Yeah? So then I get here d mu g beta alpha plus d alpha g beta mu, and minus d beta g mu alpha. And two of the terms, they cancel each other. And finally I will get the guy which goes like that. And I don't forget about 1/2 here. And yeah, basically this guy cancels this guy, and this guy goes like that. I'll get plus 1/2 g alpha beta d mu g alpha beta a mu. Right? And basically, yes, that's what I get here. I get the thing like here. Go without minus sign, because here I have lower indices here, upper indices here. Okay, it's vice versa. And then basically what it means, that what I get here is that I have the usual divergence plus 1 over square root of minus g, d mu square root of minus g, a mu. Just because that's how I do the variation of the determinants. And that's also for Levi-Civita connection, because precisely for this connection I get this expression here. And which means that I basically get something like this. And now imagine you have some divergence under your integral here. Instead of r, you substitute some kind of divergence of a vector. And then basically you have just some total derivative. Because this square root of minus g would cancel this square root of minus g. which means that in principle, if you have this Levi-Civita connection, you have covariant derivatives, you can integrate by parts. The usual way you do that with partial derivatives. So if you have your covariant expression here, you have some divergences, you can integrate by parts without much worse. So that's another convenient property of using the Levi-Civita connection. It gives you very nice properties. And yes, I also mentioned last time, because the Levi-Civita connection respects the metric, the covariant divergence of covariant derivative of the metric is 0. You can also change the position of index inside the covariant derivatives and things like that. So basically, what we have up to now, we have some kind of construction which uses the covariant derivatives. We chose the covariant derivative corresponding to Levi-Civita connection, and that means that we can use all the usual rules of integration, differentiation, and things like that. So you don't need to be careful about many things. Yeah? So derivative of the product of two things is just two separate terms. The covariant divergence gives you 0 if you have some boundary conditions, things like that. Yeah? Okay, so that's the point now. And now I come back to this action. Let me see what I get from this variation. From this variation. Let me try to do the variation of this action. And then what do I have here? Let me do the variation with respect to inverse metric. Okay? Either I take the variation of this G mu here, and I get R mu, or I take variation of the square root of minus G, how I do it here, okay? And gives me minus 1/2. My square root of minus G I put to the left here. And this guy I didn't take. I didn't touch it at all, so it goes like it was. Variation of the inverse metric. And in principle, I also have to take care of the Ricci tensor here, which means that I have here plus G mu variation of the Ricci tensor, right? So that's all I can do here. Yeah, there is nothing more I should take variation of. This guy here is already G mu, the Einstein tensor, and so if finally I manage to get rid of this guy here, then it means that I derive the Einstein equations. Yeah, because if I say that the variation of this action should be 0 for arbitrary variation of the metric, then yes, the Einstein tensor must be 0. That's what I'm deriving now, right? If I want to add matter, then yes, of course, I also put the action for the matter to the right here, right? So the question is, what happens to this variation here? And that's a funny point, because in principle, that's something which might look problematic. Why? Because if you look here, the connection coefficient, it has first derivatives. And then you define the curvature tensor, it has first derivatives of gammas, which means that you get second derivatives of the metric. And usually it's not what we want to have in our action. We want to have first order derivatives in the action, so that the equations of motion are second order. In gravity, you see, we get something different from that. And actually, why it's not so bad is just because all the second derivatives are just boundary terms. Integration by parts can just make you get rid of them. And how it happens, now we can see. Let's look here. Or maybe right here. I have this Ricci tensor here. I want to find its variation with respect to the variation of the metric. But in principle, okay, I can say that the variation of gamma I can write down in terms of variation of metric, and then I can write down the variation of each tensor in terms of gamma and substitute one into another, right? So what can I do here? I want to find the variation of R mu, and then I go like term by term. I have like the derivative of the variation of the gamma, then minus derivative of the variation of another gamma, like that. Yeah. And then what do I have here? I have quadratic terms. It's also not so difficult, but let me just write it without indices. Gamma delta gamma plus another one, gamma delta gamma. And this one, yes, taking variation of either this guy or this guy. And then minus again, gamma delta gamma minus gamma delta gamma. So you have this kind of chain here. And then, in principle, you know, this guy here must be a tensor. And here you have and you remember that we discussed last time that variation of a connection coefficient is also a tensor, because the transformation laws of the connection coefficients, they were different from the tensorial by some kind of addition which did not depend on gamma at all. So if you take some difference of two connections, it's a tensor. So this guy is a tensor. But if you take some partial derivative of this guy, which is a tensor, it's no longer a tensor. So it sounds like a problem. And we also have all these terms here not being tensors, because gamma is not a tensor. Beta gamma is a tensor, but not gamma itself. So then how could it be? In principle, if you want to have some tensorial quantity here, and instead of the partial derivative, you must have covariant derivative. And again, the guy here is a tensor. So basically you can say that the covariant derivative of this tensorial guy is just the usual partial derivative plus one term, like gamma delta gamma, one term for this index, and minus one term for every index downstairs. Again, I don't put the indices, you can do it yourself if you want. Yeah. So you do it like this, and then actually you can check that basically all this chain here is nothing but this guy. Just the covariant derivatives of delta gamma minus another delta gamma. In principle, if you write it down accurately with all the indices here, and I mean, if you want to understand how the theory works, you better do it yourself at least once. You put all the indices here. You have, you know, this covariant derivative is like partial derivative plus 3 different terms. And if you substitute here, you get like 6 terms of this kind of shape, like gamma delta gamma. And if you do it accurately, these 6 terms, like 2 of them, will cancel each other, and the remaining 4 will be precisely these ones here. So that's something you can really check. It requires maybe like 5 minutes. You sit down, you accurately use the definitions of all these covariant derivatives, you put all these terms with the indices, and then you substitute here, and you see that, yes, precisely you get the variation of this guy. Okay? Yeah? Well, it's not precisely true always, just because, you know, to see that 2 of them cancel each other and the other 4, I will have to use the symmetry. That's like gamma alpha mu equals to gamma alpha nu. That I will have to use. So otherwise, yes, it's general, and in principle, yes, if it's not symmetric, you will be able to prove that it gives you something like that, plus some contraction of torsion with this variation of the gamma. So in principle, you can always, of course, find the tensorial expression here just because that's a tensor. So there is no way it can be different. But yes, if you have torsion, you will have some extra terms. But otherwise, yes, you can either check it explicitly, or you can, you know, convince yourself that there is no other way it can go. Because if I don't have non-metricity, I don't have torsion, the only thing I have is like curvature, nothing more. So I just cannot construct anything tensorial out of that except this.
Because I remember this is the Platini equations, right?
Yes, okay. About Palatini I did not yet talk. But yes, I mean, one thing is, okay, let me say the following thing. Like, first of all, yeah, what I already have proven here means that here, yes, I have G mu multiplied by this guy. And since G mu for Levi-Civita connection is covariantly constant, I can just, induce it under the action of the derivatives. And basically this term is just the total covariant divergence of a vector. Because, I have here this thing. I multiply by G mu. So what do I have? Like G mu multiplied by gamma alpha mu. It's some vector, with alpha. And G mu multiplied by this guy here, also some kind of vector. And basically that's just the covariant divergence of a vector. And if I believe that, I can integrate by parts, then that's it. Which means that this variation does not give me any contribution to equations of motion. Yeah? So that's the usual variational principle in gravity. You can also ask yourself if it's all right to have this kind of higher derivatives here, because then to be able to integrate by parts, you would need to both have metric and first derivatives of metric to tend to zero at infinity. Then you can integrate by parts.
Yeah, but why we assume that the first derivative of the metric lies at the boundary?
Okay, then that's the point. Yes. So I mean, if you take it just as some kind of variational principle, like you say that formally, you define your equations as the ones which follow from vanishing of the variation of this action. I mean, that's your choice. What kind of boundary condition you can put there, right?
You only have two choices. One choice is the variation of the metric is zero. There is no condition for the variation of the chain.
I mean, we have to put both metric and derivative of the metric.
Why not?
Yes. Then gives you zero for the boundary terms. Otherwise, yes, it would give you something else. I mean, if for you it's just some kind of some kind of formal definition of what you call the variational principle of how you derive equations, doesn't matter. You can say your metric just with all the derivatives goes to zero, and that's it. Mathematically, you can calculate the variation and see the equations of motion. If you are going to construct quantum field theory for gravity out of that, like let's say in path integral formulation and things like that, then yes, you are in trouble because this boundary terms would matter. So then it depends on what you want to have. So I would say like if it's just some variational principle for deriving classical equations of motion, it doesn't matter how many conditions you put in the boundary. It's your choice. If you want to construct some kind of quantum gravity in path integral formulation, for example, then yes, you're in trouble. And then you have to go for some kind of boundary terms for this action, like Gibbons and Hawking. Yeah. Or if you want to play the games of like energy, momentum, and gravity, then yes, it also can play a role. Maybe Adri would mention something like that, like in his black hole lectures in the last days of the school. Okay. Yep. So that's the point, and that's if I take the variation, the metric is the only variable here. Another approach is like Palatini. Palatini approach would say, okay, let's say that metric is one variable and connection is another variable. And then, basically, which means that variation of the metric is only there, because the Ricci tensor does not depend on the metric then. And the variation with respect to the connection gives you this kind of guy. And basically, if you assume from the very beginning that the connection is symmetric, then basically this equation will give you that the connection must be Levi-Civita. If you do not require it to be symmetric, you will have something which they call projective invariance. You can change connection without changing the Riemann tensor. Yeah, so that's kind of another point here. So my aim was just to introduce the Lagrangian principle because that would be important for the discussion of numerical relativity in the next lectures. But yes, if you really want to discuss the influence of boundary terms, then yes, you have some more troubles here. Precisely because if you work only in terms of the metric, then there is no way you can write the action generally covariant and without second derivatives. So that's the point. In principle, yes, you can write down the equation of the action principle just like gamma gamma minus gamma gamma, omitting these guys here. And in principle, it also gives you the same equations of motion, but the action principle is then not generally covariant, which is also not so nice. So yes, in gravity, yes, we do have this kind of strange problem of variational principle. If indeed you are very careful about boundary terms, because in principle, there is no reason you cannot you cannot constrain the variations as much as you want. If you solve the equations of motion, then yes, you cannot prescribe more boundary conditions than needed. Otherwise, your solution just doesn't exist. But if it's just about the variational principle, I mean, you can define whatever you want, of course. But yes, if you go to quantum gravity, then that's another story. And now, let me also mention a bit about the importance of symmetries here, because, as was mentioned also today, if I just work in flat space, the usual field theories, then kind of like time translation invariance gives you energy conservation, space translation invariance gives you momentum conservation, and things like that. In gravity, actually, it's not the case because your space-time might be not symmetrical, and then which means that you don't have well-defined conservation laws, which maybe also other could discuss a bit in his lectures later. And in order, basically, the point here is that, this covariant divergence of a vector takes, some kind of nice form. And for example, if I have antisymmetric tensor, like electromagnetic field strength, it's antisymmetric. The same would be true. If it's antisymmetric, it will also be like something like that. And then yes, you can go for all the usual conservations and blah blah blah. But if your tensor is symmetric, like energy momentum tensor, then if you calculate this covariant divergence, it's not equal to anything like that. So in this sense, this kind of conservation does not imply any real conservation of some kind of integral quantities. Precisely because you have extra terms in terms of the connection coefficients. And this simple form of divergences, it only comes for vectors or antisymmetric tensor like that. For symmetric tensor, it's not true. So that's the point. But like in gravity, we also have some symmetry, which is local symmetry. Okay. And the local symmetry we have is diffeomorphism invariance. Yeah. And the local symmetry does not give you conservation laws like energy or momentum. It gives you some kind of identical relations, which do not require equations of motion. And let me just mention what happens for gravity. Okay, so basically, what do I have? I have my metric. If I change coordinates to x prime, I have the new components, and I can find out them like this covariant, these partial derivatives of the coordinate changes. Yeah, that's the usual law of changing coordinates for tensors. And how can I look at that? I can say, okay, let's say that the new coordinates x are the old coordinates x prime plus some vector psi depending on this x prime coordinates. I can do it, right? So which means that tx alpha over tx prime nu is like theta alpha nu plus derivatives of the psi, right? Then what can I do here? I can substitute the things, and that gives me like g mu prime at x prime is equal to g alpha beta at x, right? Plus I only go to the first order, plus I will have like d nu psi alpha g alpha mu plus d mu psi beta g beta mu, like this, right? So that's the difference between the two values of the metric. And I also have here the difference like in the position. Like the same position gives me different value of the coordinates. So basically I can say that g prime mu nu x prime is the same as g prime mu nu x plus psi alpha d alpha g mu, right? Just because I changed the position of the index. And then yes, finally, what I have like the variation of the g mu nu as a function of x will be given like d nu psi alpha g alpha mu plus d mu psi beta g beta nu minus like psi alpha d alpha g mu, something like that, right? So that will be the variation of the metric. The variation of the metric which comes from change of coordinates. Yeah. In principle, this kind of expression here, it's diffeomorphism invariant, even though I use just the partial derivatives. That you can check, which cannot be different just because that must be a tensor. These kind of things are those which are called like Lie derivatives, like a Lie derivative of metric with respect to the vector psi. That's one thing. Another thing, I can look at this, and I see here the partial derivatives of psi, and I also see here some term with the derivatives of metric. And of course, you can again guess that you might try to change the partial derivatives for the covariant derivatives by transforming this guy to the connection coefficients multiplied by psi. And I'm not going to do it explicitly, but then you can see that finally you can prove that this thing is like that. Just the covariant derivatives here, and this term just basically serves as two different terms from here. And now that's what I was going to say. What kind of conclusion you can make from the diffeomorphism invariant of the action? So let me see. Like if you try to derive the equations of motion, you do the variation of the action, and basically you get some kind of integral. And then let's put here what I could call partial, like functional derivative of the Lagrangian with respect to the metric. And basically your equations of motion say that this guy is equal to 0. Yeah? So you do the variation, and the thing which must be equal to 0, that's your equation of motion. But I know now that if I do the change of coordinates, I have some particular variation of the metric, which is given by the covariant derivatives here. Which means that if I substitute here this kind of variation for the metric, then the statement that my theory is diffeomorphism invariant, that the action principle is diffeomorphism invariant, it means that if I substitute this particular variation of the metric here, then this guy appears to be identically 0 without use of any equations of motion, right? Just because I assume that my action is diffeomorphism invariant. Yeah? So if I do the change of variables like that, it does not change the action at all. It leaves it identically the same. Yeah? So that's the idea of diffeomorphism invariance, so any invariance. And if I assume that, I can integrate by parts, and what do I have? I get that the covariant divergence of this guy is 0. Or more precisely, covariant divergence with respect to the first index plus covariant divergence with respect to the second index, it's 0. But this guy is symmetrical. So basically what I get from here is that the covariant divergence of the equations of motion is identically 0 without using the equations of motion. Yeah? And what it is, that's precisely the statement that the covariant divergence of the Einstein tensor is 0.
I have a question.
Yeah?
Is the last equation always true, or is only when the vector is a killing vector? Because when you do this, you will have a term that only dies if this is a killing vector.
No, that's always true. That's always true. I mean, here I'm not assuming any kind of symmetry or whatever.
Okay.
That's just diffeomorphism invariance. If I have some symmetry, yes, I would be able to derive some conservation law. The conservation which, assumes that the equations of motion are satisfied. That's when I need the killing vector. But actually, the diffeomorphism invariance assumes that I can always do that, and it's still, correct. The first order variation is 0. And yeah, and that's what we get. And indeed, the covariant divergence of the Einstein tensor is just identically 0. It does not require any killing vector or whatever. It's always 0. And basically, that's the consequence of diffeomorphism invariance. Yeah. And why I was going to also discuss that is now the last point about the gravity theory, is that then I take this 1 minus 1 over 16 pg r plus Lagrangian density for matter. That would be my Lagrangian for theory of gravity with matter. Okay? And then we define that that the energy momentum tensor of matter is 2 over square root of minus g, the variation of the matter Lagrangian with respect to the inverse net. And then after that, if I do the variation with respect to metric, I will get minus 1 over 16 pg g mu plus 1/2 energy momentum tensor equal to 0. And that's basically the Einstein equations in presence of matter. Okay? That's why I have this here. And the sign depends on my signature convention. Because if I take g mu d mu phi for the scalar field, yeah? If I have the signature convention plus minus 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 minus, I take plus sign here. And then yes, I define my energy momentum tensor with plus sign here, and I get positive energy. If my signature convention was minus plus 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 plus, then I would prefer to put minus here so that my kinetic energy is positive. But then I would put minus sign here, so that minus here and minus here compensate each other. Yeah, so the signs here, they do depend on my signature convention. And actually, if you look at the usual field theory, usually you derive the energy, the stress tensor by Noether theorem. And for simple cases like scalar field, the Noether theorem gives you precisely the same energy momentum tensor you get here, in gravity. If you go for electromagnetism, you will derive non-symmetric energy momentum tensor from Noether theorem, but you can, correct that, because if you have some conservation law like that, you can say, okay, let's take T mu nu, and I change that T mu nu plus some derivative like d alpha like S alpha mu nu. And if your S alpha mu nu is antisymmetric in the first two indices, then it doesn't change the conservation law because the second derivative would just vanish, like contraction of symmetric or antisymmetric. So like very often from Noether theorem, you get you do not get immediately symmetric energy momentum tensor, but you can symmetrize that without violating the conservation law. And the funny point is that for all the usual theories we have, the Noether theorem gives us the same as the gravity here after symmetrization. Why is it like that? Well, I mean, in principle, the first question you can ask yourself is why you have the conserved energy momentum tensor from this kind of definition. And actually, that's basically the same story as for this equation here. Again, if your whole action is diffeomorphism invariant, then if you do variation, if you do like the transformation of coordinates, then this kind of variation does not change your action at all. Okay, in principle, you will have to also add variations of the matter fields here. But if you assume that the equations of motion are satisfied, then you don't have that variations. And finally, you also see that in case, if you also take into account the equations of motion, then finally, the covariant divergence of the energy momentum tensor is 0. Which means that in Minkowski spacetime, just the usual divergence is 0. You have the usual conservation laws. And basically, you know, since usually you don't assume that you have several independent laws like that, then usually this energy momentum tensor coincides with what you can get from Noether theory. But actually, that's one of the funny points here. Like the question is whether you always get precisely the same by this approach or by Noether theorem approach, and that's something more difficult to discuss. Okay, so yes, that's what I was going to discuss today. Actually, I also was going to derive the Friedman equations, but apparently now it's too late, and that I will do tomorrow. But okay, to summarize, yeah, we have this kind of geometric foundations. I define the covariant derivatives. I define curvature tensor. Assuming zero torsion and zero non-metricity, the connection must be Ricci like here. I define Ricci tensor as a contraction of Riemann tensor, or curvature tensor. And then, yes, I construct the Einstein tensor from, oops, here was something bad. Like, you know, I had to put more accurately. But anyway, that's basically the scalar curvature, and that's the G mu nu. So I get the Einstein tensor. The Einstein tensor is always covariantly constant in a sense, like the covariant divergence is equal to 0 without using equations of motion. It's just identity. The covariant divergence of Einstein tensor is 0, identity. Okay? And then today we discussed how to get that from variational principle. The variational principle goes like in terms of this Einstein-Hilbert Lagrangian, which is very simple. Although, yes, there is this kind of troubles about second derivatives there, which you just get rid only assuming that you can require all this vanishing of both metric and the derivatives, or this for the variation. And yes, if you do that, you have this kind of action principle for gravity, which will be used later. And what I also was trying to point you at, that the symmetry, the diffeomorphism invariance, that's basically the thing which is, which is in charge of this conservation here. So precisely because your action is locally invariant under these diffeomorphisms, you get this kind of law without using any equations of motion. That's identical thing here. Okay? And yes, then you have to bear in mind that the energy momentum tensor of matter must be symmetric for you to use it on the right-hand side of the Einstein equations, because otherwise just antisymmetric part would be required to be 0, because the left-hand side is symmetric. And the usual definition of the energy momentum tensor for gravitational theories is in terms of making variation of the meta Lagrangian with respect to the metric, precisely because you want to derive the equations of motion from one action principle, like here. And yes, for all the theories we know, like the usual theories in physics, basically the same thing you can get from the Noether theorem upon symmetrization of the energy momentum tensor, which you get from there. So yes, that's the final point, and that's all my introduction to general relativity, basically. In the next lectures, I will use that to derive the cosmological things, like inflation, the cosmological perturbations, and this kind of things. But the theoretical foundations are here. Yes, so any questions? That's it.